We are now at the last part of the review. The last two problems deal with continuous functions and continuity. And let me quickly explain, like I did in class, there are going to be two kinds of problems dealing with continuity. The first is when they give a function and then they ask you if the function is continuous at a certain value of x. So you're only checking the continuity at that specific value of x. And we would do some problems like that. The second kind of problem is they give you a function and they say, here's the function. Tell us if there are any values of x where the function is not continuous. So the first kind of problem, they're asking you to go in and look at a specific value of x. Is this function continuous at x equals 2? The second kind of problem, they're just giving you the function and saying, here's a function. Look at the whole function and tell us if there's any values of x where this function is not continuous. So really two kinds of problems. So number 11 starts out where we're going to look at a function and they're going to ask us if this function is continuous at a specific value of x. So here's the original function, x squared minus 2x plus 1. And they're going to say, is it continuous at x equals 5? Now in class, I said the way to do this properly and the way you have to do it to get credit on the exam is to go through the 3 steps. So let me just go through the 3 steps and I can describe them to you as we go. The first step, you simply take the function and you plug in the value of x that you're looking at. So f of 5. So that's going to be 5 squared minus 2 times 5 plus 1. So that's 25 minus 10 plus 1, 16. Second step, you take the same function. Now we're going to look at the limit as x approaches the value of x we're looking at. So the limit as x approaches 5 of f of x. I'll go ahead and write it here. X squared minus 2x plus 1. So it's like the first question is asking, what does the function equal when we're looking at that value, when x equals 5? The second question sort of says, well, what's the limit of the function as x approaches 5? It's almost like the first part is looking at the specific value. The second part is we're looking at the function sort of around the value. We're not looking at x equals 5, we're looking at what happens as x approaches 5 from the high and the low side. So now we know how to do these limit problems. The way you start out is you plug in 5 for x and you see what happens. So 5 squared minus 2 times 5 plus 1. Turns out it's the same as right here, so it's 16. And the third question is, does the answer from part 1 equal the answer from part 2? And if the answer is yes, then it is continuous. So in our problem, since they are the same, yes, this function is continuous at x equals 5. Let's look at the second problem and see what's going on here. So here the function is x minus 25 over x minus 5, and we're checking the continuity at x equals 5. Same 3-step process. First, evaluate the function at that value of x. Or at that, So f of 5, plug in 5 for x. 5 minus 25 over 5 minus 5. Negative 20 over 0. What happens when you divide by 0? You stop and you say it's undefined. Now here's the thing. I told you the way we do these limits is the three-step process. However, like in this case, if one of the steps of the first step, if the function doesn't even equal a number, then obviously we can't compare the number from part 1 with the number from part 2 because there is no number from part 1. So in other words, we can just stop now and we can say it's not continuous when x equals 5. All right, so that happens sometimes where you're going to go through the process, but at some point when something like this happens, you can stop and say there's no reason to do the rest of it because it's not going to matter. Now let's look at C. C is interesting because it's going to be a piecewise function. So let's think about what's going to happen if we are checking a piecewise function. So negative x plus 3 if x is less than or equal to 2. So I call 2 is going to be what I call the transition point. That's sort of where the function changes. And the function equals x squared minus 3 if, oh, see, I'm not being careful. I was looking at problem D. So problem C, make sure it's correct. Negative x plus 3 if x is less than or equal to 3. And then x squared minus 3 if x is greater than 3. So sorry about that. So it looks like 3 is our transition point. And they're asking about the continuity at x equals 3. Well, I'm going to follow the same 3 steps. First step is I need to determine the function when x equals 3. But since it's a piecewise function, I have to figure out which function I need to use. So I need to go figure out which function applies when x is 3. In this case, it's going to be the top one because this is the function you use if x is less than or equal to 3. So therefore, I'm going to plug in 3 for x. So I get negative 3 plus 3 equals 0. Now, second step is the same. The limit as x approaches 3 of the function. Now here's what's interesting. If you remember how we calculated the limits of a piecewise function when we're looking at the transition point, you actually have to, in this case, look at the low side limit and the high side limit, and then you see if they're equal. And if the low side and the high side limits are equal, then that's your limit. So to find the limit for this problem, I have to do the low and the high side. So the low side, the function I use is the top function, because here I'm looking at my number is a little bit less than 3, which means I use this top function. So I can plug in 3 for x, and you get minus 3 plus 3 equals 0. So the low side limit is 0. Now the high side limit, which means x is a little bit larger than 3, I have to use the second function. So now I plug in 3 for the second function, and I get 3 squared minus 3. This is 9 minus 3 is 6. And you know what happens? Since those are not equal, there's actually not even a limit. Because you remember, right, for there to be a limit, the low side limit has to equal the high side limit. Well, in this case, they're not the same. So there's no limit for this function. So obviously, I can't compare part 1 and part 2, so I say it's not continuous at x equals 3. Sorry, you weren't seeing that. I'm not paying attention. So let me talk through this again in case we didn't see it. So to find the limit of the function when x approaches 3, since it's a piecewise function and I'm looking at the transition, I have to look at it from the low side and the high side. The low side equals 0, the high side equals 6. Since those are not the same, there is no limit. Therefore, to check continuity, I have to see if the number for part 1 equals the number from part 2, but part 2 there's no number because there's no limit. Therefore, it's not continuous. All right, let's look at D. One more of these problems where you're checking continuity at a certain value of x, another piecewise function. So this one, f of x equals, let me make sure I copy it down correctly, negative x plus 3 if x is less than or equal to 2, and then x squared minus 3 if x is greater than 2. And we're checking for continuity at the transition point when x is 2. All right, same 3 steps. F of 2. Which function do I use? I have to use the top one because that's the one that applies when f is 2, when x is 2. So I have negative 2 plus 3 is 1. So f of 2 equals 1. Now I'm looking for the limit as x approaches 2 of the function. So once again, since I'm looking at the transition point, I have to actually calculate the low side limit and the high side limit. So the low side limit, so I'm looking at values of x that's just a little bit less than 2. So I use this top function. So when I plug in 2, once again, it's 1. Now the high side limit, when x is a little larger than 2, I use this second function since it's the function for x greater than 2. So I plug in 2 for x here. 2 squared minus 3. 4 minus 3 is 1. So let's look. I'm trying to find the limit as x approaches 2. Since this is the transition point, I have to look at the low side and the high side limit. The low side limit is 1. The high side limit is 1. Therefore, I do in fact have a limit as x approaches 2 of f of x. It's 1. And now, so here's my answer for step 2. Step 1, f of 2 is 1. Step 2, the limit as x approaches 2 of fx is 1. Since they're the same, third step, I can just write down the answer. It is continuous at x equals 2. So checking continuity of piecewise functions can be a little bit of work, especially if you're looking at the transition point. So now on to problem 12. Now 12 is the other kind of continuous function problem, and that's where they just give us a function and say, are there any values of x where the function's not continuous? So look at the whole function and sort of figure out if there are any values of x where the function's not continuous. So here's the deal. The first problem we have is a piecewise function problem. And as it turns out, if we're given this function and it's a piecewise function, so 2x squared plus 1 if x is less than or equal to 3, and then the second part, 5x minus 1 if x is greater than 3. Here's the deal with piecewise functions. The only time that they're not going to be continuous is going to be at the transition point. Because if you look at this, this is just a normal, this is like a parabola. It's a continuous function, no breaks, no gaps. The other function here is like a straight line, no breaks or gaps. So nothing's going on except at the transition. And then you have to decide, at the transition, is the function the same or is there a gap? In other words, right, if we draw, so if we're looking at x equals 3, right here, here comes the first function. Now is the second function, is there a gap where it takes off? Or do they meet at the same point? So basically, all you have to do is determine the value of the function at the transition point. If the function's the same, then there are no places where the function is not continuous. It's all the same. However, if there's a gap there, then that'll be a point of discontinuity, and it'll be the only one. So it's pretty straightforward. You take the first function and you plug in 3. Let's do it like this. 2 times 3 squared plus 1, 9, 18, 19. So that first function, when x is 3, it equals 19. What does the other function equal at the transition point when x is 3? 5 times 3 minus 1. So in other words, this piecewise function is the kind that there's a gap. Because when you're coming from the low side, when you're coming in to x equals 3, the function is like approaching 19, but from the high side, it's 14. So you would say it's not continuous at x equals 3. So as it turns out, with a piecewise function, the only place it might be not continuous is at the transition point. So once we check it, lo and behold, we found out it's actually not continuous. Let's look at this other problem and see what's going on there. So another piecewise function where we're asked to determine are there any points where it's not continuous. 2x squared plus 1. So here the transition point is going to be, looks like 1. And here's the other function, 5x squared minus 2. If x is greater than 1. So 1 is your transition point. So the only possible point in this whole function where you might have a break or a gap is your transition point. So I'm going to simply check the value of the function at x equals 1 for both functions. So for this one, when you plug in 1, two times 1 squared plus 1, this is 2 plus 1 is 3. For this one, I plug in 1. 5 times 1 minus 2, it's 3. So the function coming from the low side, it's approaching 3 at the transition. The high side, it also approaches 3. Since the transition, the function is the same, that means there's no breaks, gaps, or jumps, and no points of discontinuity. In other words, the function is continuous, the whole function. There are no gaps or breaks. All right, now, very last problems, we're still checking, we're given a function, we're asked to find out the values of x where the function is not continuous. Now the only other time we have to be concerned is, now this case, it's just one function. It's not piecewise. And let me write it out, and then let me tell you what we're going to be looking for. So 10 minus 3x squared over x squared minus x minus 20. When you're given a function and you're asked for this function, find any values of x where the function is not continuous. There's only one occurrence where it's going to happen, and that's if the denominator equals 0. If the denominator can never equal 0, then that's going to be a place where there are places where the function is continuous. There's going to be breaks or gaps in the function. So all I have to do is look at the denominator. In this case, I have a denominator. In this case, I have to see what values of x would cause the denominator to be 0, and those are going to be my points of discontinuity. So in this case, I have to factor it. It factors into x minus 5 times x plus 4. So I know x cannot equal 5 or negative 4. What that really means is these are the points of discontinuity. These are the points where the function is not continuous. And that's because those are the values of x that cause the denominator to be 0. The function cannot exist wherever the denominator is 0. So it turns out there are two values of x where this function is not continuous. Okay, the very last problem, we're given a function and we're asked what are the values of x where this function is not continuous. Well, what's interesting is whenever you have a function, the only time you're going to have places where it's not continuous is if you ever have a 0 in the denominator. Well, look at this. It's not even a fraction. It's not even a rational expression. Therefore, it doesn't make sense to talk about having a 0 in the denominator. There is no denominator. So I don't really have to do any math. I just say it's all continuous. This whole function's continuous. There are no values of x where that function is not continuous. All right, that should finish up the review, so I hope that helps with some of these problems.